Well, good
Welcome,
morning.
and
Afternoon.
thank you
Oh,
for joining us.
sorry. We'll play the video here. Apologize.
Welcome, and thank you for joining us for this webinar presentation. We are the Defense Systems Information Analysis Center, or DSIAC, one of 3 IAC domains in the DoD Information Analysis Centers operating under the Defense Technical Information Center, DTIC, within the Office of the Undersecretary of Defense for Research and Engineering. Our informative webinar series highlights current and emerging research and technology developments. It presents an opportunity for accelerating the DoD's leverage of these advancements by increasing awareness and fostering technical collaboration. DSIAC serves as one of the premier information research partners and curators of technology advancements and trends for the defense systems community. As such, our organization supports those working in the defense systems domain of DoD research and engineering. We do so by helping navigate the vast landscape of scientific and technical information, allowing our customers to get a head start on their technical projects. With an understanding of the defense system's DoD research and engineering landscape, we provide research and analysis services. We help unlock access to information, knowledge, and best practices from government, industry, and academia to stimulate innovation, foster collaboration, and eliminate redundancy. We hope you enjoy this webinar presentation and that it serves as a catalyst for community collaboration and improved DoD defense systems research.
All right. Well, good morning, afternoon, evening, wherever you might be dialed in from and joining us from. Thank you for joining for this month's the DSIAC webinar. I'm pleased to have Frank to be delivering the presentation. And before we begin, just a couple points of housekeeping with respect to this webinar presentation, the platform that we're in. First of all, I guess comms check. Hopefully some folks, you all can hear me. I think my microphone was working a moment ago. But my name is Brian Benish with DSIAC, the Defense Systems Information Analysis Center. And with respect to this any meeting platform, first order of business is that at any time during the presentation, if you have a question that you would like to pose to Frank, I would ask if you could enter it through the audience questions portal or form. You can find that through the little message icon located at the top center of your screen if you are in the AnyMeeting platform. Unfortunately, if you're dialed in, you won't have the ability to submit your questions. But what we will do at the end of this presentation is go through a little Q&A session. We'll have all the queue of questions up, and I'll help moderate them, and Frank can respond. So again, any questions you have, please enter them into the Q&A portal. I do want to distinguish that from the chat, which would be on the left-hand side of your screen. Please refrain from putting your questions there. If you do accidentally drop them there, we'll make sure they get in queue with the formal Q&A section. But other than that, I will say if you drop out for any reason, have any technical difficulty, rest assured this is being recorded, so you can access them. We'll make the video available at a later date. And then secondly, the slides should be available or becoming available shortly through the website. So if you do have any other difficulties, you can grab the slides from there and use the dial-in number to follow along that way. Other than that, the general format will be handed over now to Frank for his presentation, and then I'll jump back in at the end for the Q&A. So Frank, the floor is yours.
Thank you, Brian. Good afternoon, everyone. This is Frank Zahiri coming to you from Warren Robins Air Logistics Complex at Robins Air Force Base. 402nd CMXG is the commodities maintenance group that I work for. I manage the industrial process control coordinator here at Robins Air Force Base, also at Warren Robins Air Logistics Complex. In addition to that, I also help and support the technology development, acquisition, and insertion and transition within the Robins Air Force Base and across multiple other Air Force Sustainment Center air logistics complexes, including Tinker and Hill Air Force Base. I have also had the opportunity to work with across the Department of Defense with our friends and colleagues from NAVAIR, NAVSEA, and our friends from the Army on multiple projects. So today, what I intend to provide to you is the topic of advanced manufacturing strategies and technologies and the Warren Robbins ALC's paradigm. And I'm going to begin with the CMXG technology insertion goals. I'm going to read the bullets actually, and as I go through the set of slides that I have provided, we'll see if what I have identified or we have identified as goals, are we aligned with all of the technology options that either are developed or we are developing? Are we en route or on a map or in the right direction to achieve our goals? So for that, I have the one that is most important, which is advanced analytics for smart manufacturing systems, to be able or be the enabler and enhancer for resilient to disruptions and uncertainties. And pretty much you all know what resilience are. Given the certain disruptions can happen, we can still continue on working and delivering as contracted or as promised. Increased factory visibility to make sure that we have a control over our throughput and flow days. Those are the key performance indicators for us. Near zero defect and downtime performance. So that goes back to our ability to make sure that the products that we produce are to the requirements and compliant with the specification and standards. And all of the support machinery that is helping produce that product is actually up and running with the highest uptime possible to achieve our goal of zero defects and the lowest downtime possible. Worry-free production, that's a mouthful what worry-free production is. But at the end of the day, our expectations are based on our knowledge and visibility to our production system availability, which is all of the machinery that support us, to the business system and logistics and supply chain transparency. We can then coordinate a production planning and a scheduling that works across the board with as I said, scheduled such that all machines are loaded based on the required demand and can operate and execute to produce parts. And the second enabler, actually, industrial artificial intelligence, AI, and machine learning for smart predictive manufacturing. Another one of those that you could fit maybe hundreds of technology options in there and you be okay. And the enhancers would be the predictive analytics for machine health monitoring, diagnosis, and prognosis, and the greater assets availability for lowering the operating cost. That means being more efficient in our execution. So the goal is to properly balance the efficiencies, balance the effectiveness. That means we're producing parts to the requirements. So cost effective readiness, so effectiveness and the cost, and then meeting the schedule of performance. So those three nodes of performance, that is our ability to meet the requirements, schedule, which means we deliver to our promised dates, and cost, which is within what we expected to be or anticipated or calculated for those costs. So with that, let me just go in. Now I have to give credit to plenty of my collaborators to put this picture together. It's just a picture for now, but I will describe to you why it's more than that. So I put this architecture or framework together with support from multiple academic professors, including Dr. Tom Kerfus of Georgia Tech, including Professor Jay Lee of University of Cincinnati, and the one who has put me on the map, I should always recognize, Professor George Vaxivanis of Georgia Tech. So with that, and I cannot forget our friends from National Institute of Standards, where I really learned on the topic of smart manufacturing. And Dr. Tom Kerfus, that the picture he brought in that bring in and fuses smart manufacturing and digital manufacturing together, what it takes to get there. So that was just to call on all those who have helped put this framework together for us. So if you look at it and you look at on the left-hand side of your screen, you see smart manufacturing. On the right-hand side, digital manufacturing. With the smart manufacturing, our concentration, at least for now, is all of the production system, right? All of the machinery equipment. And what do we want to do that? So we want to be able to manage and have a repair management system. We want to know the detail, the structural state. So as we sell our product to our customers, which are weapon systems that we manage here at Robbins Air Force Base, including C5, C-17, F-15, Global Hawk, you name it, right? And across the DoD components, we also produce parts that are friends from NavAir and F-18 use. So knowing the state of as maintained product that we are producing and providing to our weapon system. So smart manufacturing, just concentrating on the infrastructure and machinery to make production or enable production. The digital manufacturing side on the right-hand side is mostly related to model-based engineering, model-based design, the CAD, CAM, all of that you are all on this line familiar with. So moving toward model-based, moving toward control over, let's say, product lifecycle management processes under the what they call MROIs, right? The maintenance, repair, and overhaul, the next generation of that. So using models as the way of going forward and using the smart manufacturing concept. But here now you have to fuse this to remember to achieve the goals that I mentioned, including the predictive analytics and machine health monitoring, advanced analytics, greater asset visibility, meeting the product specification. So what did we decide right in here was right in the middle. We had to have ability to capture information, especially for our machineries. But at Robbins Air Force Base, just to throw a number at you, we're modernizing our machining center, the environment. We have over, let's assume, close to $100 million worth of assets for production purposes, just as in the machining centers. So to be able to shift the paradigm into a condition-based maintenance, we had to bring a conduit, a platform to capture all of the data that we are receiving, either from the machines that are censored to and instrumented to provide those health data to us, or the ones that are legacy and we are to install instrumentation to be able to capture the data. So we had to bring in an IoT platform which will help us to produce or enable us to have digital traceability, enable us to have industrial connectivity, enable us to have IoT in the loop, as you well know, with the industrial Internet of Things, right? So we're moving that way. We're also having projects such as augmented reality, assisted reality, virtual reality that we have on board, either for training purposes or to support in the digitalization of assets and seeing them in their virtual environment or cyber twin or virtual twin, right? And then we have multiple projects that says, okay, all of that data that comes in from the IoT platform, where do they go? So now we have algorithms developed, applications developed for failure prediction, right? Those monitoring dashboards or knowledge bases, I rather call them, rather than a dashboard, is to show us the state of our machinery and how we got where we got, right? It's important to be able to trace back how did we get here. And then if you look at the top of the picture, you see the concept of IoT analytics. So we have data analytics, using some of the big data analytics. Are we there yet? Maybe, maybe not. Artificial intelligence, are we there? We are moving toward those. And I will get to some of the projects that are really supporting that IoT analytics box that you see there. And then digital twins. I will get to the digital twins on the next slide as I go forward to see the scope of the virtual environment that we are creating. So you get a picture of how we use those enhancers or enablers, such as the data-driven basis, the multi-physics approach, in modeling, and then ultimately as a support for our decision process, right? Supporting and enabling. And then you see at the bottom connectivity to hopefully the OEMs and the PLMs, the products lifecycle management, and other government systems of record. With that, now, as I promised, it's time to go into a CMXG digital factory and to see what I meant by creating those digital twins, cyber twins. I have to credit here again Professor Jay Lee out of University of Cincinnati. Believe it or not, when we started this route to smart manufacturing, it started actually some 15 years ago at Robins Air Force Base when I was working with Dr. Vaxavanis out of Georgia Tech. Parallel with him, I was also collaborating with Dr. Jay Lee out of University of Cincinnati. And I believe at the time, the machines that we instrumented at Robins Air Force Base for health monitoring, a 5-axis machine, we were one of the few in the United States approaching that, trying to bring in and establish condition-based maintenance as a paradigm shift from a scheduled maintenance and what have you, or recommendation from the OEMs, rather on condition-based maintenance. So a paradigm shift some 15 years ago. At the same time, I believe Professor Jay Lee was running along parallel to us at the Harley Davidson factory. So that was that goes back 15 years as it's been built. So this graph actually, or this picture, will show you that as a test bed that I have, and I'm going to mention the test bed is a prop blade for the C-130 prop overhaul process. So what we have done here is actually created a test bed. And if you recall from the picture I showed you before, which was the framework for our advanced manufacturing, I showed you on the left-hand side the smart manufacturing concept. So to get to that smart manufacturing concept, we referred back to the NIST, National Institute of Standards documentation. Professor Lee's the concept of connecting and converting and cyber and cognition and configuration, the concept of cyber physical system, smart manufacturing. So if you look at the left-hand side of this graph, when we talk about the maintenance and we talk about cyber components, we talk about cyber machines, all the way to the cyber production line, this is exactly where I said the smart manufacturing plays for us, where we now here try to take what physical assets look like and try to see if we can bring them to life or a mirror image of them into a virtual environment. So if you look at, I will present to you today in this upcoming slide what we did with the cyber component, let's say an atomizer that we remove coatings from, let's say, the blades of the prop for the C-130s and the issues that we had with the main component, what we went through to get that virtual equivalent or cyber twin of that blade and or that component, the nozzle that forces water jets to be able to remove those let's say plastic goods or rubber goods from the blades, right? And then you will see the cyber of a machine. That means a $5 million machining centers that we took over, saw every one of the modules, and we did actually translate those modules in its virtual based on the, let's say, degradation modelings that we did. Every modules in that machine, from the control system to the hydraulic systems to the spindle system, we characterized them based on their performance. They're based on their lifing methodology, and some based on the drawings that they have. So the structural identity. So the models that we created referred back to the structures and the behavior of the machine. So those two different domains and dimension in our creating the cyber of the machines and the cyber of the components were in the back of our mind. And then we said, okay, now at the middle, the interface where you come from the right-hand side, where you have the model-based drawings, the model-based engineering, and you have all of the CAD, all of the CAM, all of the computer aided engineering in place in your production for the parts, and then doing those models exist, or we're moving toward that model based environment. And then the cyber process, which is, let's say, path planning purposes, if you are to produce a part based on features that are defined in the model, right? So being able to simulate those path plannings, optimizing them such that we do not create any type of, let's say, if you're machining them, any type of crash as it goes through those limits of the machines, the feed and the speed that is required. So we calculate all of that in a cyber environment or in its virtual simulated environment, and then produce that in the production line. And you say, okay, Frank, give us a little bit about the production line cyber. What have you done there? This is where we brought in multiple products from OEMs. In this case, again, I'm not marketing anyone. In this case, we actually brought in the capabilities of taking an entire production line and creating the point cloud exactly what they are. So we use the Faro arms, the pictures or what have you, to be able to position every asset, every machine, everything that moves through that line into a cyber environment with XYZ IJKs identified for each element, right? And then what we did, we overlaid that on top of the AutoCAD drawing of our shop floor. That was done to see how we get toward virtual manufacturing or reconfigurable manufacturing. How do we optimize our production line? Where are, again, for the purpose, as remember, cost-effective readiness and production and being effective in our producing our parts, right? So to be able to reconfigure our manufacturing processes and activities, we had to bring that. So a capability, a point cloud definition of our entire production line for the prop overhaul process, overlaid on the drawings of the facility. And then now you can move any elements or any parts or any process that are being executed. Then you can move all of those based on the recommendation of your process engineers, your production line employees or technicians input in how best to reconfigure the work. And if you look at, for example, one of the benefits, now you say, okay, Frank, what is the benefit? One of the benefits actually gained from what we did through this reconfigurable manufacturing was an immediate saving of over $3 million of ability to identify what we are going to condemn as part that it goes through the process of 120 different activities, right? So very clear and present return on our investment, which was that dollar I mentioned. And then not only that, ability to generate new dollars. That means ability to induct more prop into the process, right? So that required a balancing, as far as I said, balancing of the flow days, optimizing the throughput, modifying such that we can, in that simulated environment, we can run optimization, we can run the simulations and be able to then achieve what we want. So this is the picture, right? When you refer back, why create that digital twin or the cyber twin of your production line? Why do you want? Because we don't necessarily can touch the assets per se, but we can actually do troubleshoot before getting to an asset in that virtual environment. With that, let me just move on to the next topic of smart manufacturing. And I hope that I just gave you this story that sets us up for key enabling technologies, predictive maintenance, and digital twin framework. Now I'm going to get hopefully a little bit more on the technology options and our approach. With that, let's go to the next slide, which kind of shows how, I guess, everyone got here. But this is where Dr. George Vaxavanis and I sat for 15 years following and benchmarking against the best of them out there. put this picture together. I'm not saying that this is done by us, but then again, this is ultimately where we want it to go. And that was in clear here in this picture, predicting the future health of a component so that maintenance is done based on the actual material condition of the component. So that was, we had to go through this scale or path or roadmap to get from a repair or replacement broken. I'm not saying that that's not justified still, but then again, we are moving toward that predictive and prescriptive maintenance actions. So with that, just put the picture together that you can see the roadmap. So if Dr. Vaxavanis would say in most of my project, we sense and monitor, right? So that is the most important part. We model and mine. So we do create models. We do the simulation for the model mining purposes. We detect, right? Detect is where diagnostics and prognostics will happen. And ultimately, what it all does to us is to support our decision. So detect and decide at the end, right? So this decision could be either autonomous, as what Professor J. Lee would say at some point, reconfiguration of, let's say, a control system on autonomously, or man in the loop being able to change that, or would be, again, helping support recognizing and the cognition purposes of all of the data that we're having and being able to know what will happen next and what to do about it. So this picture, it says a lot, but then again, it requires capabilities to deliver that. And so let's look at the next slide, which hopefully is predictive maintenance. What does it say? It says building trust, confidence, and risk mitigation in predictive maintenance. So that's to us an enabler. Innovative technologies, the enhancers for that are data analytics, data mining, data pre-processing, feature extraction, detection, and fusion, right? So these are words exactly from Dr. George Vaxavan. So I go back and I say, okay, we built, not words just don't, they're not listed here as we take action on them. When we say data mining, we produce ability or we develop abilities or we bring on board data mining capabilities. Data pre-processing, we bring in analytics and AI in feature extraction and detection, right? And then data fusion, I actually will show you a project on data fusion where we move toward a self-aware machine, and we'll get to that. Fault diagnostics, which we have developed now, as I said, if you look through the what I said, the troubleshooting purposes through a virtual environment, now we can reduce, for example, the time to troubleshoot from a day to 4 hours to 4 minutes, right? So be able to troubleshoot and in the simulated environment and then take that as the way forward as we go to see the physical assets. So we want to be able to do an intelligent move toward and identifying the asset's status prior to getting to that asset. Then failure prognosis, accurate prediction of time failure. That has always been an Achilles heel of our projects. So I'm not going to claim that we're there, but I do claim that after 15 years, we are getting pretty close, though, very close. Based on all of the latest capabilities in machine learning and AI, we are getting closer in being able to predict when a component or a machine as a system as a whole will go down, and then being able to or being enabled to then adjust the production planning and the schedule to meet the current state of our machinery, and then ultimately define the optimum maintenance strategy. So with that, let's move into those old concept of asset reliability centered maintenance. What is the foundation, right? The foundation that we had to have in place to build on sense and monitoring, modeling and mining and detection and deciding, right? It has to be built on a foundation, and that foundation is based on the mathematics and the physics and the statistics of things. So expressing the percent confidence that system asset can execute a mission, task, over a designated period. So this wasn't to be built on just empirical numbers. It had to be built as in a combination as physics, as math, and as data driven, as depending on as the complexity of the system increases, our choices are now either go and spend as much of resources as possible to create those physics-based models, or rely on what we know on based on the data as a virtual sensor. So data-driven models should come into the game. And ultimately, as we're moving toward a goal-driven strategy, right? So as the systems are getting more complex, so we're moving towards that. But all of that and all of that set is we're building it based on the physics of it, which is here reliability under stress, fault condition. One system more reliable than the other. The method fit the data to a suitable life distribution. And I said lifing. Remember, I said one of our damage assessment and evolution as we go through the process of detection and deciding, and ultimately that prognosis that said they remain in useful life. So with that, and the statistics, as you saw, you're all familiar with the asset reliability and the statistics there. And so let's move in a little bit more detail, reliability and life cycle management. So again, another one of those repeats of enhancers, data and data mining, prognosis, first order, higher order reliability methods, optimization tools for optimum maintenance strategies, risk assessment. So risk is very important here, right? A day of imagine if there are multiple machines are down here at Robins Air Force Base, an aircraft may remain on the ground. We will not be able to deliver what we promised to the warfighter. So there are tangible costs and there are intangible ones or implied ones. Here, the implied ones. So it's important that we are in an environment that we know of the risk and we can manage accordingly. So with that, we move to a predictive maintenance reliability-based architecture, right? So, and here is that atomizer I just mentioned that, one of the methods that or techniques that we're using in that creation of the digital twin of that component on the atomizer, right? So an engineering system you're looking at, we are developing the life loss modeling, right? So degradation modeling, all the stresses, the prognosis and remaining useful life, ultimately knowing the safety and all of the analysis of safety. So anything that we touch, we must consider all elements of risk and including safety of both the machines, the people, and what its effects and influences are. And ultimately then trying to do a life cycle optimization. And how do we achieve that? And this is under the risk control. If you look at, depending on, changing risk profile through proactive maintenance and upgrade. So you got to remember when we change a component on a machine or modules of the machine, that machine's behavior most likely has changed. So therefore, it's not what we started with again. So we got to remember at all time when we develop those models are behavioral, also representative of the structures and their interactions as we go. Take corrective action with acceptable risk, quantify risk and uncertainty, essential links between failure prognostics and reconfigurable control. So in that reconfigurable control is we have now started developing control system for next generation machineries, right? Being able to have ability to spontaneously respond in a high frequency environment. So we enable autonomous decision making. That means if there is, let's say, an issue with our machining or the G code that's generated for the machining center to make an operations, and it's not calling out certain access system on the spindle system, or speed and feeds are not right, we have the ability then for the machine to be able to make judgments on, okay, should it stop work? Should it identify? Should it raise an alarm? Should it create a fault? And if it does, can it really reconfigure or configure itself to say, okay, now it's time to stop, or wait for the reprogramming that rather than the 3 axes that are being used, and applying forces on the spindle system, which is beyond what's expected. Let's see if we can use the 5 axes and reduce those stresses. That has actually happened. That has happened at Robins Air Force Base, and we were able, not autonomously, but the data that we produced from the machine, we captured from the machine, led us to be able to modify the execution of the program or the model that we delivered and the G code that we provided to use multiple axes rather than just the 3 axes on the machine and reduce the stresses. And we wish at some point for the machine to give us that ability. So, next slide. Ingredients for success. What do I need in order to apply predictive maintenance technologies? Again, predictive maintenance, let me just bring that up. So in the world of things happen, we always go back and say, okay, why did it happen? And now that you know why it happened, you don't want it to happen again. So what do you place in? You place in the monitoring that says you want to know what's going on now. Now that you know what is going on now you have to have all those applications and algorithms to be able to kind of predict what will happen next, right? So you don't want to get an unanticipated, blindsided what happens next. And then ultimately the Achilles heel is prescribing now what you should do about it if it does happen. So as what Dr. Baxamanis would say, data, ground truth data, sensor and sensing strategies, computing and communications, modeling, algorithmic developments, and the smart bridge between the real and virtual world. And I think you want to concentrate on the next one, which is that's where I'm going next, on the smart bridge between the real and virtual world. So just to put it in perspective of cost and optimization based on cost effective readiness at all activities that we do. So application of enablers, sensors and sensing requirements, health and usage monitoring, communication and computing. Now that's easily said. So to be able to do all of that communications computing requires to bring in information technology, systems of record across, at least in the government environment, bring those data from the IT world, fuse them with the OT worlds, which are mostly operational technology data, which are mostly time series type data. How do you bring the metadata and fuse it with the operational data, right? Zeros and ones and zeros, right? How do you do that? So those are the challenges that we face. Just saying health and usage monitoring, it isn't just like that, or computing requirements. So currently we work on, let's say, a data fabric project, right, that intends to achieve that. Modeling of physical systems, I explained to you, that's what we do right now, currently on, at least on a test bed and the platform that we have at CMXG. And then what Dr. V, I believe the grandfather of dynamic case-based reasoning, the bridge between the physical and the virtual or the digital twin, and then ultimately try to put it together in a cohesive and coherent picture and implementable. So we just at least try to show from the physics-based, the reliability center type maintenance, where the foundation is built, the new tools and applications that we are bringing on board, developing those cyber or virtual twins, referring back to all of the standards from the National Institute of Standards, National Science Foundation, having multiple academia, multiple small business and large business actually involved in the execution of this program. So with that, let me just give a definition of a digital twin as we see it. There are multiple other definitions for sure, but this one I like to refer to. A digital twin is a virtual representation of a physical object or a system across its life cycle, using real-time data to enable understanding, learning, and reasoning. I can say that real time, we are not there yet. I can tell you with the systems that we have, we can operate near real time. And those are the challenges that we have: getting connectivity, being able to get the real time data. That is still remains as Achilles heel for us. So imagine you have, let's say, 50 machines that you need to connect, and you need to connect it into a network, and that would be on a platform, IoT platform. Have that data be generated and being able to real time do the analytics on the data, and then alarm if there needs to be alarming to the shop floor to take action based on what you get, or at least do your algorithms for the predictions. So just have that in the back of your mind that it, for us at least, it hasn't been that easy to get to the real time data, but we're close. We can present near real time data even now that we're working. So with that, I guess now we're getting into uh, the functionalities of digital twin. Improving maintenance decision making, as I said, the damage prediction, reliability modeling of physical system, that is in a simulated environment, either based on the physics of it or based on data-driven models, or a hybrid of physics guided data-driven or goal-driven models, right? System lifecycle mirroring, supporting decision making and predicting system performance. For example, in the AR projects that we have at Robbins Air Force Base, we are creating a mirror image of the spindle system on a T4, which is a 5-axis machine. So we can, if there needs to be repair done, we know every structural component. We can bring that in a virtual environment to the technician with all location specified X, Y, Z, I, J, K defined, so they can find the items or elements or modules that repair is needed for. They can establish all of the parts associated with that, and then the instructions how to do it. Not only that, they can also communicate, in this case, real time, with someone from the OEM or from someone from the our maintenance organization to get direction on what's next. So ability of bringing a mirror of the spindle system without even opening up any components there, and then identifying based on what I said through the virtual twinning, through your expert troubleshooting that you did in the simulated environment. Now you have the mirror image. Now you have the entire asset in its three-dimensional view as an augmented reality. So you can work it before you get to the part, or work it as you are there to locate where things are and you need to repair or make your repair or execute your repair or task you need to do. A statistically based decision making and optimization. As I said, we brought in the entire virtual of our production line, our test bed for a prop overhaul process. We virtualized that. We were able to modify actions and activities, so we could therefore update our work control documents, which describes every step of the process. And then as a one enhancer, be able to reduce at least the number of operation that we do on a part that ultimately will be condemned. So I can just tell you, you can imagine that a blade, I'm just giving an example, just a number, may have to go through 2 miles of travel from induction to a completely going back on a prop assembly again. So how do you optimize this process to help flow days, to reduce bottlenecks, to optimize the throughput? So all of those things requires, and there are multiple variables and parameters involved. So that is where the computer systems come into the game to be able to do those analytics, right? I believe any person can manage 3 or to 5 things and see the interaction amongst them. But if you increase all of those variables, then there is a factorial change in in the number of things that can happen, and therefore computers are best to do that, and algorithms that we are developing help us get there. And then digital twin modeling aims to assist lifecycle management of assets. That's just given. So, and that is what we're using it for. Key benefits again. So at every step of the way, as we do, we have to prove return on our investment, right? There is no free money anywhere. We have to be able to show return on investment. So the return on investment should be through improving operations, integration of asset information and history to be able to actually, if nothing else, based on the past, you could look at the rear view mirror and potentially see what is happening or what will come up next, right? You unify asset management processes, extend asset life cycle, optimize maintenance work processes. So when I say we have modernized into about 75 or 70 plus $million of new assets, what we are doing now, we are bringing on board enablers and enhancers to make sure that our maintenance activities are up to par with what needs to be done now, based on our usage, based on the degradation modeling that we have developed. So we attend the machine when we must, schedule the machine for maintenance when we should. So with that, and then ultimately prescribing what needs to be done, right? So with that, I'm going to jump into the digital twinning and reference back a few of our projects just in the area of smart manufacturing, just in the left-hand side of that framework that I showed you. So with that, I referenced the contracts that are supporting these projects. So they're mostly through the SBIR program, Air Force SBIR program. Some also have funding from OSD R&E. Some are plus-ups from NAVAIR. So this is not just one DoD components doing it all. Actually, we try our best to make sure that we get projects that are enterprise-wide and capabilities can go across the DoD components. So here, though, is one of my projects as that we bring multiple capabilities, both as physics-based driven, where we use ANSYS modeling of a water pump, to data-driven, and then hybrid of the two. Actually, there's not a technical publication on this topic in the IEEE that you could look up. So what we did here was creating a pump digital twin requires building its accurate 3D model and powering the model with data. That's where we capture. So we had to actually put sensors on board because this is a legacy system. We had to put sensors on board to capture the data, create those living models, create the anomaly models that we appear or abnormalities that we see in the operations. So therefore, structure and the behavior. Putting the digital into action, the digital twin-based predictive maintenance. So that's motherhood and apple pie after all what I've said on pump failure modes and criticality. So we wanted to have a signature of that pump. And here you go. Water pump digital twin using ANSYS. So ANSYS for the modeling purposes on the physics of the pump. And then you on the left-hand side, you really see that pump in the operation. Those are actual. The pump digital twin that we created, another actual as part of the project. And the Achilles heel now is bringing the physical world to the virtual world and making sure that we can act on the physical world based on what we learned from the virtual environment. So that is where the data analytics, data streaming, history, all of those things come into the game. I'm not going to mention any of the enablers as companies who supported us in this endeavor, right? But you can reference back again. You can reference back to the organization and the Air Force contract that we executed the program if you wanted to learn more. And here is dear to my heart, actually, the machining center's digital twin. I see that I've missed another, although I referenced Dr. Christopher Bowman of DFNN, I missed to acknowledge my work with and their work with the company QSI here in developing the digital twin for our machining center. Remember, the goal here was to create a $5 million asset, all of its module, bring it into its virtual environment, and try to do expert troubleshooting, try to see based on the behavior of the machine, develop the degradation modeling. And then ultimately, the challenge to Dr. Bowman was always, okay, we want this machine to be self-aware and be able to tell us what we need to do about it, or at least help us in that. So with that picture, I guess it says a lot of words. I mean, 1,000 words. In this project, we also have a great collaboration going with the ARL, Army Research Lab, on the equipment to be able to monitor the current and voltages and to see spikes. And you say, why would you do something like that? And that is to look to see if we can identify potential intrusion in our systems or be able to, there are multiple views to this, behavior of the machine based on the loading and the structure limits of the loadings and what you have, but also is there a possible of cyber intrusion and how do you identify that, right? So that was again another part of making our machine smart. And if those voltages and currents, those waves, can we make sense of them? Can we find abnormalities that will lead to anomalies, that will lead to a failure of a component or a failure of the machine? So yeah, as I said, you can read more. We have a couple of technical publications actually in reference to these projects. You can look them up at at the time of your convenience. So the solution architecture for the real-time Makino, I believe you can see that. So it did take, and I have to also acknowledge here the work of AFWorks in funding us for this project, right? So AFWorks, AFVentures, they have been critical in providing us funding to be able to support this, right? At the Robbins Air Force Base. They also see that these potential solutions as we go forward, it is not only Robbins Air Force Base, you got Hill Air Force Base, you got Tinker, you got the COM-FRCs for the Navy. So all of them have these machines that are supporting production lines and producing and helping produce parts for the aircrafts or weapon systems that they manage. So with that, as we build this architecture, as we bring in the health monitoring, as we bring in those apps or applications or algorithms for intelligent decision making. So again, or the ability to virtualize an entire machine in a computer world or in a cyber world is what the challenge was, and we have been delivering. And then ultimately, now we get to the AI ML toolbox, right? So how does this AI works, right? What is this AI? What is artificial intelligence? What is machine learning? What do you guys do? So a picture of what we do and how it all operates. You're very abstract, but you can always, I don't know if it's time to go through the detail of this abstraction at this stage, but again, I have put the references, I have put the contracts number. They're open to publics, right? They're open. They're published progress reports. They're published summary reports. They are published papers that you could refer to. And as we advocate, and this is one of the projects actually we are working jointly with NAVAIR, not only on a shop floor on machinery, but also on weapon systems such as C-130s and C-5s that are looking into exploiting this capability, right? Not only that, this project actually came to us. Some of these projects came from the Joint Space Operations. So credit to them that they started the topic years ago before we were even in the field of identifying capabilities for AI and ML. With that, let me move on to the next slide and the next process, right? So AI-driven digital twin benefits. I think you can read most of these. I think the slides will be presented to you. So unknown abnormal precursors to detection enables reduced cost. Very good. Real-time equipment asset health monitoring. Yes, as I said, if I have access to the real time, but I have near real time access currently, our expectation is when we have our IoT platform up and running, we will have real time data to be able to, right? So then let me highlight visualization of the historical events, right? Those are highlighted in AI driven benefits. Can be utilized designing and deploying a cyber physical fault tolerant resilient system, the model based engineering. So, all of that we are enabling through the project. At least the minimum we do is we learn and we then try to scale and tailor to other requirements. With that, AI ML toolbox. I want to get into this another project of mine that is just give you a background on. I see my time is up or getting close to, but I'm just gonna. Too bad I have to rush through this one. So this is where the concept of machine vision, computer vision actually came about. So a blade, a taper board of a blade requires inspection, whatever that looks like. And you'll see the pictures, hopefully. I have the slides. So we have to take with a borescope over 400 pictures. Those 400 pictures need to be analyzed by technicians. That takes a little bit of time in the hours, like say a couple of hours, right? To be able to detect any potential damages or deformities or nonconformities that may lead to potential disasters, right? So being able to do that, it takes 450 plus pictures that needs to be maintained and kept forever, and also recommendation on a damage map of what have been, and then ultimately the decision from the ESA or engineering authority that says, okay, this is good, or no, other repairs needs to be done, or condemn the part, right? That took a lot of time. That just in that cell, in that operation, in that function. So what we did along with Georgia Tech, along with a company that is referenced in this report presentation, we were able to bring on board an ability to take that 4 hours, turn it into 4 minutes using AI capabilities, right? So using deep learning algorithm such as convolutional neural nets, right? So excellent work that is a combination of work from Georgia Tech and our friends from Analatam. This actually was one of the projects presented at the NCMS CTMA competition. We were ranked very high in that. So I let you read the as I am time it's short in time, but I will let you read this. But now this is coming back into our where it is getting integrated with our ability to capture data as point of maintenance. As we move toward our digital transformation, we have developed the architecture, the roadmap for this transformation. And one of the fundamental requirements was capturing data at the point of maintenance. And here, not only we can capture data at the point of maintenance, but also we can complement it with AI, ability to detect, ability to then help the technicians to go from being in the loop to on the loop as an executive monitor. So with that, I think the approach you can kind of basically look at. There are also publications on this, and again, I cannot forget the support from Georgia Tech and the technical publication from Dr. Tom Kerfus and Dr. Chris Saldana and Ivan Wren, who was my principal investigator on this project. With that, I think the last slide will give you the solution benefits and reduction in maintenance cost, which was specifically for this project actually 75% and greater. So that was the return on investment and cost effective readiness. That just clear and present savings in the work that we do. And then ultimately you have the intelligent digital twin that we are looking at. So AI-driven digital twin approach in predictive maintenance. I think you can read this slide. I mean, there's just a statement there as our experience and the concluding comments, which are data, referring back to what we have learned from the past 15 years. High fidelity system modeling, and the system modeling, both the structural, behavioral, moving from a physics elements when we can't, and it's difficult, moving to a data-driven models or a hybrid of the two. And then prognostics, predictive, and as we move to prescriptive maintenance. With that, I thank you all for listening to me. And if we have time for questions, I took so long, so I appreciate that. Thank you.
Yeah, Frank, no, that was a fantastic presentation. I definitely want to leave some time for questions that came in along the way. Yeah, I do recognize that we're long on time here, but for those who can stick around, I would love to go through some of these questions and hear what you have to say about them, Frank. And then for those who do have to drop off for time constraints, again, we are recording this, so you could always go back and listen to it if when you get time. So if that's okay with you, Frank, I'd like to go through a couple of these questions.
Good. I'm here. Yes.
Okay. Yeah, let me go ahead and put them up here. All right, so first one's asking if, and I'll just reread these for those who are dialed in, but are you implementing the systems shown in the CMXG advanced manufacturing slide on the on-premises systems, or are you also using GovCloud infrastructure?
Yeah, excellent question. So yes, we are using on-premise. So we have on-premise cloud servers that is put on here at Robins Air Force Base. We have not yet moved into Cloud One or Platform One, but are we aligned and architecting the structure such that we can get there? Absolutely. So we look to other organizations within the Air Force Sustainment Center to guide us toward that. So I can always refer back to the Air Force Sustainment Center's Information Technology Office. They're the ones that are leading and informing us of the right approaches, and we follow their leads. Great question.
Very good. All right, thanks. Another question here from Ram, specifically about one of your earlier slides on the evolution of maintenance practices slide. Said, wondering if you were saying that CBM is from the context of the work piece, but not from the process equipment itself. Could you clarify?
Oh, so there has been a disconnect on this question. CBM, I look at it as at this stage of the game, for the CBM, I meant truly the infrastructure or the machine. So we are doing the health monitoring of the asset, being the machine itself that does the production activities. I did not cover anything as far as the processes that goes through execution of a part from raw material to its final product. That comes in next. If I get an opportunity to come back to present, that would be our real-time process monitoring, which we are moving towards. And we have developed all of our process failure mode and effect analysis as part of ensuring the quality of the products that's been produced by our machines. So I should have made that clarification. CBM is specifically for the machinery on the shop floor, and then in-process monitoring are my projects that are on the right-hand side of that framework that says model-based manufacturing and digital manufacturing. I hope I clarified.
Yeah, no, it makes sense. Thanks. Okay, next question. Noticing that some of the tools and methods that you described or were described here were, say, roughly 30-year-old in the U.S. industry. Are these new to the Air Force, or for the academics?
Absolutely not. I refer back. This is a great question, though. I think the algorithms that we are developing is the state of the art. So yes, again, methodologies cannot change, can remain, but methods do change. We develop techniques. So the algorithms that processes gigabytes of data in a matter of milliseconds, I don't think it was there 30 years ago. I've been at this for 15 years, so I can't refer back to 30.
Yeah.
But I'm not challenging the question at all. I'm not. I can just tell you that when we started 15 years ago, I remember all machines that were producing parts had no sensing system per se and no data that was useful to us from the SCADA systems of the machine. Now every machine that you buy comes in with those sensor systems. So I think we were instrumental in moving and informing the producers that the market actually demands machines that come in equipped with those sensing systems. And as I see it in the future, the next 15 years is actually machines that will do reconfigurable on autonomously. Not only that, but also they're capable of giving you the digital twin of every one of those modules within that machine. So yes and no. Thank you.
Okay, that's good. All right. Well, the next question is asking: are the manufacturing platforms or systems in the DoD are there manufacturing platforms or systems in the DoD currently that are able to perform real-time data collection or analytics?
Yeah, we can do real-time data collection. That's for sure. I can do that already on the shop floor. But the analytics is I have to push that data to our analytics engines, right? That is not yet there.
Yeah.
So yes, again, great question. We are able to capture the data in real time. Being able to do the analytics in real time, we're getting closer. Not there yet.
Gotcha.
So very good question.
Okay, next one asks, is the digital twin rooted in the initial engineering models?
Okay, now let's bring the perspective, put it in not necessarily looking at a part, but looking at the machines, right? You could say some of the models that we have that we get from the OEM that are used for, let's say, simulation purposes, yeah, to a certain degree. But I don't know that we have those initial engineering models. If you refer back to the drawings, we may have some 2D drawings available to us, not necessarily any models per se. Are we able to translate some of those 2Ds into a 3D environment? Surely we can. We have projects ongoing right now at Robins Air Force Base that we are able to do that. But is the digital twin rooted? The answer is ultimately, yes, but we are enhanced by that. So we are enhancing it through the data that we are capturing from the service environment, right? The behavior of the machine or the component as we go forward. So do we rely ultimately on that model that existed in a 2D drawing and all of the physics and mechanics of that? Yes. Are we also complementing that with all of what we capture from the sensings that we have on board to complement? That is a yes too. So I hope I answered because I don't specifically know engineering models. Because when you say models, I look into point clouds and the model-based environment. We do not have that. There may be some. Yes.
Well, on that same train of thought, another question was submitted, same person here, about the digital twin, asking how are desirable high-performance immature technologies, typically without complete qualification data, how are they accounted for in the digital twin?
So we are trying to, get our best view of things, right? So in creation of our degradation modeling. So we based on data driven. So if you ask me, Frank, has all of these digital twins and AI that you guys are developing, or you're saying that is in the process been through a rigorous, if that's rigor process of test and evaluation? I like to refer back to the joint DoD AI and say, hey, we are working on that. Actually, we have defined and articulated projects that will help us get there to be able to have the most confidence in the recommendation that comes from the AI tools, right? So, and the digital twins are the best that our modelers can model, right? So as I said, the best that we can model based on the data that we receive as they are fused or complemented by the physics of it, if available. So qualification data, that is a very, very good question. So therefore, I'm going to claim that we will be there someday.
Yeah.
So for verification and validation and confidence and bringing your high confidence level or developing a confidence level high enough to really rely on just the AI and not have the human as an executive monitor on the loop. So I'm not there yet to make that statement. Thank you.
Okay. I think we had two more questions in queue. So one out of two left here asks, are you using data, in quotes here, are you using data knowledge graphing to represent or expose the next best action type alerting?
So this is a great question. Whoever produces it, they very much know of the knowledge graphs and ultimately semantic modeling and making sense of multiple sources of data being fused in one location for business intelligence, for operations intelligence. Absolutely, we're moving that. As a matter of fact, I'm sitting at Hill Air Force Base here on our data fabric project. So excellent question. Are we moving toward that? Yes, we are. Are we moving into developing the semantic models that brings and makes sense of all of those graphs and connectivities and the mutual connectivities of those nodes and linkages? For sure we are. Excellent question. That is our next. Yes.
Perfect. Okay, and then last question we have here. Are you leveraging learning from other industries, such as the automotive sector, regarding intelligent production machines and tagged parts, RFID, and similar identifiers, for maintaining a digital thread throughout the part life?
So these questions are coming from people who I think have transparency to my projects. Absolutely. So we are bringing RFID projects, right? Exactly here for do asset monitoring on the shop floor, right? Excellent question on that. So we have RFID in the process. We are grateful to AFWorks, actually AF Ventures, to providing funding for us. So we coordinate all of that projects, not only at Robbins Air Force Base, but also through the Air Force Research Lab, right? So we don't disconnect, and we are aligned and linked with our definition of digital twin and digital thread. We rely back to AFRL, right? Air Force Research Lab. We follow their leads. Yes. Do we benchmark against the best of them in the auto industry? For sure. Absolutely. If you look at the robotics automation that we have a subject matter expert involved completely in that. So yes, we are looking, and I just can claim this one. I think within the depot maintenance organization, I recognize that our robotics and automation is ahead of many other organizations, and that's given to the support that we receive not only from the OSD, not only from the SAF AQD, but also from multiple manufacturing innovation institute that support us on those. So yes, good questions. We benchmark and we probably borrow others' capabilities. Next.
Oh, very good. All right. Well, hey, that was the end of our questions, and I would ask for if there's any more, you can put them in queue. But we are over time, and spent a lot of time here, Frank, with your discussion, with your presentation, which was fantastic. I want to respect your time, so we'll
Thank
end
you
it
very
there.
much, everyone. Appreciate your time, Brian.
Yes, thank you so much. It was very, very good presentation. A lot of great questions, good dialogue. I look forward to any future discussions and questions we might be able to generate from this. So again, thank you, Frank. Thank you to everybody else joining in, and have a great rest of your day.
Good day. Thank you. Bye-bye.
Bye-bye.